ambiguous. And then down on the bottom, you have your end users. So these are people who are sending transactions to the network and actually kind of using the network for their own purposes. So the users submit transactions. What I'll call the processors, miners or stakers, depending on what your permissioning scheme is, apply those transactions to some kind of database, and then so-called full nodes maintain the blockchain state, and also can actually check that the processors are doing their job correctly. They verify the sort of state transitions that the block processors propose. And users then essentially just send their transactions to miners, and frequently just get information from full nodes. We'll get information from full nodes, let's say. Some of them are full nodes themselves. Some of them just sort of delegate trust to full nodes. So let's look into the life of a full node. So here is a full node. This is, let's say, 2009. Everything's great. You download your blockchain. It's very small. Obama just won the presidency. You're happy, or at least not so sad. And yeah. So okay. So you're chugging along. Bitcoin, it's cool. One day you wake up and suddenly the blockchain is really big. You're like, oh crap! But I wasn't expecting it to be this big. You start to get a little nervous, and then as the years go on, you find yourself dwarfed by the giant blockchain, which is now consuming your entire hard drive, and that's not a great state to be in. And so this is the life of a full node. What does the life of a typical end user look like? It's more like this. There's this giant blockchain. They kind of throw their hands up, and okay. So the underlying problem here is that many end users already basically do no validation. So the resource requirements and complexity of running a full node mean that most just don't. It's intensive to run a full node on a computer. It's gigs and gigs and gigs, and it's impossible to run on mobile. And so what do? You delegate trust to a third party, be it a full node, which is like an online wallet, say, or to miners, which is how light clients work. So it would be really great if we didn't have to do this, right? I mean, this is cryptocurrency. The idea is to be able to actually verify things, not have to delegate trust. It would be nice if there was a way to be convinced of the current state without having to see the history of that state, right? I mean, it seems kind of silly, doesn't it, that you need to send somehow the entire history of a state to check the state. Who thinks it's silly? I don't know. It seems kind of silly to me. Okay, 2 people, 3 people. Okay, so what to do? So this is kind of the basic idea of how Coda works. You have these processors, block proposers, produce proofs that in fact they are applying blocks or say transactions correctly to the database. And then instead of having end users check the transaction history, the blockchain, they can just check the proof. Okay? They don't have to see the transactions, they can just check the proof. What does it prove? It proves there is a transaction history, there exists a transaction history, or I know a transaction history, which, when applied correctly to the, say, genesis state of the world, results in this state, whatever this state is. This is the state that they're trying to convince you of, the current state. The proof should be small, it should be easy to check, and so it should be a SNARK, right? We know what SNARKs are. I had a slide, but I took it away. I don't know if that was a bad idea. Does everyone know? People are. Who knows what a SNARK is? Okay. Maybe they're small proofs, right? We know. Okay. So, great. So the idea here is that you can get a sort of a full node level of security while only downloading a few kilobytes. And we'll get into what are in those kilobytes maybe in a second. So just a note, processors still have to store the current state. So of course, well, maybe not of course. It's possible one could cook up a scheme where this wasn't the case, but we didn't. Someone has to store the entire state. So that's the processors. But they don't have to store the history, and end users don't have to store the state at all. They just need this little proof. Okay, so let's try and make this a reality. Our first attempt will be somehow to use one SNARK for each block, and we'll see how that goes. So here's what we do. The processor produces a SNARK while applying the their transaction, well, say a block or a transaction to the database. Oh, I kind of screwed up my transitions. I'm sorry. This is now the database of accounts. Before it was a blockchain. You know, last night I realized that I used the same icon for both, and I was going to change it, but it was late, so I hope it's OK. We can remember that this is in database now. This isn't a blockchain. It's just kind of the current state. Does that make sense to everyone? OK, cool. OK, right. So this block, let's go back. So this block producer, you can see it's our friend. Maybe it's Bitmain or something. Produces this proof, and you know they hold it up. They look at their beautiful self-portrait. I guess they made themselves look a little bit better in the picture than in the reality. But this is the proof that they produce, and basically what it says is, I know a block which, when applied to database 1, results in database 2. Does it make sense? OK. Or simply, you can get from DB1 to DB2. That's how I'll say it, because it's too hard to say, I know a block which, when applied to database 1, results in database 2. OK, cool? And so now you have this little picture. It's not really clear what good this did. You know, maybe we could have sent the block, but this is a SNARK, so it's 1 kilobyte. In this world, you know, what happens for the end user? The end user gets this proof saying you can get from database 1 to database 2. They also check, let's say they're interested in knowing their balance. They also get a Merkle path into database 2. So say DB2 was really the Merkle root of database 2. Does it make sense? Everyone with me? OK. And now they can check their balance. So what does it mean? It means that they can be assured of their balance without having to see the diff, sort of the data diff between database 1 and database 2. They just need to know that sort of the Merkle root of database 2, and maybe they already knew that database 1 was valid. But what if they didn't know that database 1 was valid, right? I mean, what's up? Oh, someone sent it to them. You know, that guy with horns sent it to them. OK, cool. So, right, so this would be great if they already knew what database 1 was valid, but you know, it's a cryptocurrency. They just came online. They don't know that yet. So you could think, OK, well, maybe we can chain these proofs together, right? So I have one proof. It says you can get from database 1 to database 2, or 0 to 1. Sorry, I guess this is very computer science. I have another proof which says you can get from database 1 to database 2, then one that says you can get from database 2 to database 3, and then one that says you can get from database 3 to database 4. OK? And now you can look at this and you can be convinced that you can get from database 0 to database 4, right? Because you know there's these intermediate transitions. So this would be a win if this sequence instead of using this instead of a sequence of blocks, if it was smaller than a sequence of blocks. So it could already be a win, but we don't have to stop there. And this doesn't sort of solve this fundamental problem that the chain grows linearly with time. So one day, we'll all be sitting in a pile. We'll all be buried under a pile of these proofs still. OK, so here's attempt 2. This is you use one SNARK for the entire blockchain, and this is what we actually do in Coda. The basic idea is this. It's so cool. It's this idea of recursive composition of proofs. It's really an insane idea, and well, I hope you think it's interesting. OK, so the process of checking a SNARK, well, that's a computation. You can certify computations with SNARKs. So that means you can certify this computation itself within a SNARK, right? The process of certifying a SNARK, verifying a SNARK. Which means we can sort of chain multiple SNARKs together to get one SNARK, which stands in for all of them. And I'll explain in a more detail how this kind of plays out. Right. So we saw we had a little proof that said you can get from database 0 to database 1. And we had a little proof that said you can get from database 1 to database 2. So the idea is we sort of wrap these two together in one big SNARK, which now says, I know a SNARK, which gets me from database 0 to database 1. And I know a SNARK, which gets me from database 1 to database 2. OK? Well, actually, it doesn't say I know a SNARK that gets me from 0 to 1 and 1 to 2. It says I know some intermediate state so that I can get from 0 to that intermediate state. And I can get from that intermediate state to 2. Does it make sense? Is this picture confusing? Who thinks it's confusing? No one. I don't believe it. One person. 2 people. OK. Sorry to single you out. OK, 3 people. Anyone else? No. You think it's confusing? OK, well, tell me why. Is that mean? No. Oh no. Do other people agree? Maybe I should have just not used images. Some people like the images. Okay. So let's see. So right. So before, we sort of observed this fact about the world that we had these two proofs, and these little verifier guys put their thumbs up and said these proofs were good. So we can sort of capture that fact with a SNARK. We wrap those two facts together. Does that make sense? SNARKs, you can sort of freeze dry computations in some sense. Does that metaphor appeal to people? So, okay. Yeah, so you have this computation which happened once, and you sort of freeze dry it for all time. You sort of take a photo of it, or a little movie, or maybe a comic, I don't know. And sort of, what's the word? Sort of solidify it, congeal it. Yeah, what's up? Oh yeah, that's equals. It's just saying, there's some intermediate states there. They're sort of hidden, but they happen to be equal. Maybe to each other. Maybe this was too confusing. It's like I can get from 0 to 1, and I can get from 1 to 1. Okay. How much time do I have? 15 minutes? Oh, that's great. Wow, I'm going fast. Yeah. Yes. So it's actually Merkle root of database. Does it make sense? And then it's great, because then at the end of the day, you have something which is certifying the Merkle root. You can just get a path. Cool? Everyone? Very vigorous head nodding over there. Okay. Yeah, what's up? Yes. Okay.
This only tells me that the path is a valid extension from the beginning. It doesn't tell me that it's the one that there's general consensus on.
Well, so this database doesn't only have account data in it. It also has sort of chain strength data in it. So if someone presents you with two proofs, you can pick amongst them by using Nakamoto consensus rule.
So for that,
does it make sense?
For that to give us Nakamoto consensus, it doesn't just require the length, but it requires some kind of prefix check.
There's no prefix check, but you can bake the chain strength into this state, and then you just pick amongst those proofs that you see. You pick the one with the strongest chain. It's the exact same as traditional cryptocurrency. Maybe let's not dwell on it. I want to finish this explanation. So, I can explain how. Yeah. So Derek can explain it later. So. Right, okay, so we saw we could chain these proofs together. That's really cool. So we do it twice. We go from 0 to 2, and then we go from 2 to 4. Okay, we had these 4 proofs. And now, wait for it, you know what we're going to do next? We're going to go from 0 to 4 by sticking together these 2 proofs. We check these 2, now we can stick them together, right? Cool? We make another bigger proof on top of it. So you see at the bottom, there's our chain receding into the distance, sort of at the bottom there, with this sort of chain of proofs, tree of proofs kind of on top of it. Does that make sense? Great. No one said yes. I don't know why I said great. Great. So it's a SNARK. So this whole thing is still 1 kilobyte, even though it's now standing in for 4 blocks, or is that right? 4. Yeah, 4 blocks instead of 1 or. Okay. So what does this look like for the end user? They download a 1 kilobyte blockchain SNARK, which proves you can reach state 4 from the Genesis state, the state with Merkle root 4. They download a roughly 20 kilobyte Merkle path into that state to get their account info. That's a Merkle path. And at the bottom, they can see at this Merkle path, I have $17, for example. That's cool. What's the upshot? Well, for the end user, what it looks like is you basically sync from nothing to sort of full node security with around 20 kilobytes and just a few seconds. This is in contrast to the typical verification mechanism for cryptocurrency. So that's cool. So let me say a little bit. How much time do I have? I went so fast. I really overestimated how long these slides would take. Yeah. Oh, wow. OK. I hope people are like short talks. So how can we kind of do this in practice? Or what's necessary anyway? Let me say a little bit about what sort of things are necessary to do this in practice. So what does a snark actually prove? OK, here's what it proves. It proves there exists a sequence of updates. Let me call them updates. I mean blocks, but let me just say updates. For some reason, it helps me to think about it more abstractly. Which, when you apply them to the genesis state, results in some state S, OK? What's in a state? This maybe will make your question more clear. I don't know. A state has the Merkle root of the current account database, the hash of the previous state, how good is this chain? So this, if we're using proof of work, this would be the accumulated strength of the chain. Information, oh, we're not using proof of work, so information for checking the proof of stake. And an update has some information for proof of stake, so kind of the information for permissioning. If you're using proof of work, this would be the proof of work. That has inside of it, some VRF evaluation, some numerical computations. So a new account database Merkle root, so the update says, what do I want the database to be after applying this update? And a sort of a transaction proof, which says, I can reach the old Merkle root from the previous one. OK, so what sort of computations do we have to do to make all this possible? OK, so we need to check a signature for each, inside of the snark for each transaction. We need to do hashing, that involves hashing, maybe some elliptic curve cryptography. Oops. And a whole bunch of other stuff. But then, we need to check balance. That involves arithmetic. We need to do stuff with Merkle trees. If you want to work with fees, we do some kind of trick involving signed arithmetic. You need to put a snark verifier inside of a snark, et cetera, et cetera, et cetera. The point is, it's kind of complicated. So maybe the overlapping of this slide indicates the complexity. Who thinks so? Maybe? No, I don't know. Oh, that's like a verifiable random function. It's not really important. I just wanted to put a lot of words on this slide to make it look complicated. Yeah. It's sort of like a cool way of injecting randomness into whatever. So the application is for injecting randomness into proof-of-stake blockchains. But OK, cool. Everyone agree it's complicated, right? Oh, how am I going to do this? Constraint systems, libsnark, I don't know. So this is a complex program for sure. But what do we do? What do we do here? So OK, so snarks essentially what they do is they certify the execution of programs. Coda's snark is a pretty complicated program. I mean, the picture looks complicated enough. I assure you, as a program, it's even more complicated. Complex programs demand high-level programming languages. Maybe there are some C hackers in here who disagree with me, but I assert. Why? Well, you need to be able to check programs' correctness, especially in an application like this. If it's not correct, it's like it doesn't mean anything. And also to actually write in the first place. So I have never, I'm not that good at writing very low-level programs. Personally, I can't do it. So for me, I needed it. Some other people need this too. I don't know. Why? Well, OK, so you want to be able to give your program structure. You want to be able to kind of make some kind of abstraction. And you also want to do some kind of composition. Otherwise, you're working with sand, essentially. So I just want to say a few words. How many minutes do I have? Oh, I'm good? OK, great. You don't know. I'm going to take a long time on this slide. OK, so I want to say a few words about Snarky, which is our DSL, or domain-specific language, for programming with snarks. What's cool about this, it's a very simple, well, in theory, functional programming language. You basically have functions and types and some kind of abstraction for modeling the non-determinism of snarks. I really think it's kind of like the core, the sort of like conceptual core of like what snark programming, at least in the real DSL is like a little more complicated, but somehow the core of the DSL I think is like the conceptual core of snark programming. And I talked with T-Bolt, who's talking after me at Socrates, and he said they've kind of like landed on something roughly similar, so maybe there's something to that. It's still for those of you who are worried about counting constraints, relatively close to the metal in some sense. You can do abstraction with minimal cost. It uses algebraic effects to model non-determinism. Probably no one here knows what that means. OK, one person. Which I think is a kind of a conceptual way of modeling non-determinism. And also, this is really important, makes it possible to sort of test, at least empirically, the soundness of your SNARK. It makes it very easy to sort of stuff junk witness data into the SNARK and see if your constraints still pass. Does it make sense? It's implemented as an embedded DSL in OCaml. Who likes OCaml? How many French people are here? No? OK. Yeah. And you can find it on GitHub. So it's github.com/o1-lab/snarky. And that's pretty much it. If you're interested or curious, please talk to me. And you can find more information on codaprotocol.com. I guess I'm not supposed to take